Download this code from codegive.com, link in the description below. Recursion for Beginners, a comprehensive guide with code examples. Recursion is a powerful and elegant programming technique where a function calls itself within its own definition. While it can seem daunting at first, understanding recursion opens up a new way of thinking about problem solving and allows you to tackle complex challenges with concise and elegant code. This guide will walk you through the concept of recursion, its core principles, and practical examples to get you started. 1. What is recursion? Imagine a set of Russian nesting dolls, matryoshka dolls. Each doll contains a smaller version of itself until you reach the smallest, indivisible doll. Recursion is similar, it's a process where a function breaks down a problem into smaller, self-similar subproblems and solves them by calling itself until it reaches a simple, solvable base case. In essence, recursion involves two key components. Base case *, a condition that stops the recursion. Without a base case, the function would call itself infinitely, leading to a Stack Overflow error. The base case represents the simplest instance of the problem that can be solved directly. Recursive step * the part of the function where it calls itself with a modified input that moves closer to the base case. This step breaks down the original problem into smaller, more manageable subproblems. 2. The core principles of recursion. To understand and implement recursion effectively, keep these principles in mind. Self-similarity *, the problem should be definable in terms of itself. This means you can break the problem into smaller instances that are essentially the same problem but with different inputs. Base case * always define a clear base case that will eventually stop the recursion. This is crucial to prevent infinite loops. Moving towards the base case * each recursive call must bring the input closer to the base case. This ensures that the recursion will eventually terminate. Trust your function *, a key mindset shift is to trust that the recursive calls will correctly solve the smaller subproblems. Your job is to focus on how to combine the results of these recursive calls to solve the original problem. 3. A simple example, calculating factorial. Let's illustrate recursion with a classic example, calculating the factorial of a non-negative integer. The factorial of n, denoted as n, is the product of all positive integers less than or equal to n. For example, 5 equals 5 * 4 * 3 * 2 * 1 equals 120. Here's how we can define factorial recursively. Base case * if n is 0, then n equals 1. 0 is defined as 1. Recursive step * if n is greater than 0, then n equals n * n1. Here's the Python code. Explanation * 1 factorial, n, function * takes an integer n as input. 2 base case, if n equals 0 if n is 0, the function immediately returns 1. This is our stopping condition. 3 recursive step, else if n is not 0, the function returns n * factorial, n1. This is where the recursion happens. It multiplies n by the result of calling factorial, again, but this time with n1. This continues until n becomes 0, at which point the base case is reached. How the recursion unfolds: 4 factorial, 5. 1 factorial, 5, returns 5 * factorial, 4. 2 factorial, 4, returns 4 * factorial, 3. 3 factorial, 3, returns 3 * factorial, 2. 4 factorial, 2, returns 2 * factorial, 1. 5 factorial, 1, returns 1 asterisk factorial, 0. 6 factorial, 0, returns 1, base case. Now, the values are returned back up the chain. 1 factorial, 1, returns 1 asterisk 1 equals 1. 2 factorial, 2, returns 2 asterisk 1 equals 2. 3 factorial, 3, returns 3 asterisk 2 equals 6. 4 factorial, 4, returns 4 asterisk 6 equals 24. 5 factorial, 5, returns 5 asterisk 24 equals 120. 4. Another example, Fibonacci sequence. The Fibonacci sequence is a series of numbers where each number is the sum of the two preceding numbers. The sequence typically starts with 0 and 1, 0, 1, 1, 2, 3, 5, 8, 13, 21. Here's a recursive definition of the Fibonacci sequence. Asterisk base cases asterisk. Asterisk Fibonacci, 0, equals 0. Asterisk Fibonacci, 1, equals 1. Asterisk recursive step asterisk. Asterisk Fibonacci, n, equals Fibonacci, n1, plus Fibonacci, n2. Here's the Python code. Explanation asterisk. 1 Fibonacci, n, function asterisk takes an integer n as input, the index of the Fibonacci number we want to find. 2 base cases, if n equals 0 and if n equals 1. If n is 0 or 1, the function returns 0 or 1, respectively. These are our stopping conditions. 3 recursive step, else if n is greater than 1, the function returns Fibonacci, n1, plus Fibonacci, n2. This is where the recursion happens. It calculates the nth Fibonacci number by recursively calculating the n1, th and n2, th Fibonacci numbers and adding them together. Important note about Fibonacci and recursion asterisk. While this recursive implementation is clear and demonstrates the concept, it's not very efficient for larger values of n. It repeatedly recalculates the same Fibonacci numbers multiple times. Iterative approaches, using loops, are generally much faster for Fibonacci calculations. 5. A more complex example, sum of digits of a number. Let's consider finding the sum of the digits of a non-negative integer recursively. For example, if the number is 1234, the sum of its digits is 1 plus 2 plus 3 plus 4 equals 10. Here's the recursive logic. Asterisk base case asterisk. If the number is 0, the sum of its digits is 0. Asterisk recursive step asterisk. Otherwise, the sum of the digits is the last digit plus the sum of the digits of the remaining number, obtained by removing the last digit. Here's the Python code. Explanation asterisk. 1 sum underscore of underscore digits, n, function asterisk takes a non-negative integer n as input. 2 base case, if n equals 0. If n is 0, the function returns 0. 3 recursive step, else. Asterisk last underscore digit equals n%10, calculates the last digit of n using the modulo operator, %. Asterisk remaining underscore number equals n//10, removes the last digit of n using integer division, //. Asterisk return last underscore digit plus sum underscore of underscore digits, remaining underscore number, recursively calls sum underscore of underscore digits, with the remaining number and adds the last digit to the result. 6. When to use recursion. Recursion is particularly well suited for problems that can be naturally broken down into smaller, self-similar subproblems. Some common scenarios where recursion is useful include Asterisk tree traversal asterisk navigating and processing data in tree-like structures, example binary trees, file system directories. Asterisk graph traversal asterisk exploring nodes and edges in graph structures. Asterisk divide and conquer algorithms asterisk algorithms that break a problem into smaller subproblems, solve them recursively, and combine the results, example merge sort, quick sort. Asterisk mathematical functions asterisk defining mathematical functions recursively, example factorial, Fibonacci. Asterisk parsing asterisk analyzing and interpreting data structures like expressions or grammars. 7. Tail recursion and optimization. Tail recursion is a specific form of recursion where the recursive call is the very last operation performed in the function. In some programming languages, like Scheme and Haskell, compilers can optimize tail recursive functions into iterative loops, avoiding the creation of new stack frames for each recursive call. This is called tail call optimization. Unfortunately, Python does not perform tail call optimization automatically. Because of this, deeply recursive functions in Python can still lead to stack overflow errors. If you need to process very large datasets and encounter stack overflow issues with recursion in Python, you may need to consider using an iterative approach or a different programming language that supports tail call optimization. 8. Iteration versus recursion. Both iteration, using loops, and recursion can solve similar problems. Here's a comparison. Feature iteration recursion. Implementation uses loops, example for, while, function calls itself. Readability often more straightforward for simple tasks can be more elegant and concise for complex, self-similar problems. Memory usage generally lower, as it doesn't create new stack frames can be higher, as each recursive call creates a new stack frame. Performance often faster than recursion can be slower due to function call overhead. Stack overflow less likely to cause stack overflow errors can lead to stack overflow errors if recursion is too deep. Choosing between iteration and recursion asterisk. Asterisk if the problem is naturally iterative, example looping through a list, iteration is usually the better choice. Asterisk if the problem is naturally recursive, example traversing a tree, recursion can be more elegant and easier to understand, but be mindful of potential stack overflow issues. Asterisk for performance critical applications, iteration is generally preferred due to its lower overhead. 9. Common pitfalls and debugging tips. Asterisk missing base case asterisk the most common mistake is forgetting to define a base case. This leads to infinite recursion and a stack overflow error. Asterisk incorrect base case asterisk even if you have a base case, it might be incorrect, leading to wrong results or infinite recursion. Asterisk not moving towards the base case asterisk ensure that each recursive call modifies the input in a way that brings it closer to the base case. If the input doesn't change or moves further away from the base case, the recursion will never terminate. Asterisk stack overflow errors asterisk if your recursion is too deep, i.e., the function calls itself too many times, you might encounter a stack overflow error. This means that the program has run out of memory on the call stack. To fix this, you might need to asterisk simplify the problem or use a more efficient algorithm. Asterisk increase the stack size, but this is often a temporary solution. Asterisk use an iterative approach instead of recursion. Debugging recursion asterisk. Asterisk print statements asterisk add print statements at the beginning and end of your recursive function to track the input values and return values at each level of the recursion. This can help you understand the flow of execution and identify errors. Debugger use a debugger to step through the code line by line and inspect the values of variables at each step. This is a powerful way to understand how the recursion is unfolding. Visualize draw a call stack diagram to visualize the recursive calls and how they relate to each other. This can help you understand the structure of the recursion and identify potential problems. 10. Conclusion. Recursion is a fundamental concept in computer science that can be used to solve a wide range of problems. While it can be challenging to grasp at first, understanding the core principles and practicing with examples will help you master this powerful technique. Remember to always define a clear base case, ensure that each recursive call moves towards the base case, and be mindful of potential Stack Overflow issues. With practice, you'll find that recursion can be a valuable tool in your programming arsenal. Good luck.